Imagine moving at 250 kilometers per hour deep beneath the ocean floor. Above you, millions of tons of water, cargo ships crossing, constant pressure, and yet, inside it feels completely normal. So the question isn't how this works. It's why this is even possible, because what makes this possible isn't just the tunnel itself, it's what happens before it's even built. And once you see that, you realize the hardest part isn't going under the ocean at all. For most of history, the ocean wasn't something you crossed through. It was something you went around. Bridges had limits, distance increased cost, and water introduced pressure instability and unpredictable geology. Digging beneath it meant dealing with all of those forces at the same time. High pressure, constantly shifting materials, and the risk of sudden flooding if anything failed. At a certain point, the challenge wasn't engineering anymore. It was the environment itself. So instead of trying to resist it, modern systems are designed to operate within it. This is China's Gintong Undersea Tunnel, stretching over 16 kilometers with more than 11 kilometers running beneath the seabed. It connects Zhoushan Island directly to the mainland. Before this movement depended on ferries or indirect bridge routes, limited capacity, weather delays, fragmented travel. This tunnel removes all of that. High-speed rail moves directly under the ocean without interruption. What used to be a disconnected region becomes part of a continuous network. This means the ocean is no longer a detour. It becomes part of the route. But building through water isn't the challenge. What happens beneath it is. This isn't built like a traditional tunnel. It relies on machines designed to operate as self-contained systems underground. Tunnel boring machines, hundreds of meters long, carrying thousands of tons. They don't just dig. They cut through rock, remove debris, reinforce the structure, and seal the tunnel at the same time, all in a continuous process. Because stopping is not an option. Once excavation begins, the system has to maintain stability under constant pressure. This means construction never stops. It continues as one system. But when the ground itself keeps changing, how does the system stay stable? Beneath the seabed, conditions don't stay consistent. Granite, clay, sand. Each reacts differently under pressure. Some layers are stable. Others shift or collapse under stress, which means the system can't operate at fixed settings. It has to adapt continuously. Pressure inside the machine is adjusted in real time to match external conditions. Too much force, and the structure destabilizes. Too little, and water can break through. So stability isn't maintained by strength, it's maintained by balance. This means the system doesn't fight the environment, it matches it. But even if everything stays stable, how do two tunnels meet without missing each other entirely? The tunnel is built from opposite directions, two independent systems moving toward each other through solid ground with no direct line of sight. And at this scale, even a microscopic deviation becomes critical. A misalignment of just a few millimeters at the start can expand into meters over several kilometers, which means the system cannot rely on fixed coordinates alone. Because underground, there is no stable reference point. Instead, position has to be recalculated continuously as the machine advances. This is done using a combination of inertial navigation systems and satellite-based correction. China's Beidou system provides external positioning data with centimeter-level accuracy. But that signal doesn't reach the machine directly once it's deep underground, so the system works in layers. Above ground, precise positioning is established. Below ground, inertial systems track every movement, every rotation, every deviation from that reference. Even the smallest shift is detected instantly and corrected before it can accumulate. Because the goal is not to fix the error later. This means precision isn't achieved at the end. It's enforced continuously at every meter of the system. But if everything is built with this level of precision, can the system even be separated again? These machines can't simply be removed. They're too large, too deep underground, and fully integrated into the structure they create. By the time excavation is complete, the tunnel has already been built around them. Removing the entire system would mean dismantling sections of the tunnel itself. So instead, engineers reverse the process. Internal components are extracted. motors, control systems, and high-value equipment are removed piece by piece, but the outer shell remains. Locked in place as part of the tunnel's structure, what started as a construction system becomes a permanent element of the final design. The machine doesn't leave the tunnel, it becomes part of it. This means construction doesn't just create the tunnel, it stays inside it. But if these systems stay in place once they're built, what happens when they're used everywhere? The Gintang Tunnel isn't an isolated project. It's part of a larger system expanding across China. And beyond that, even larger concepts are being planned, including undersea tunnels stretching over 100 kilometers. Projects that would cut 8-hour journeys down to less than 1. At that scale, the challenge isn't distance anymore. It's continuity, maintaining stability across extreme lengths under constant pressure, and ensuring that movement remains uninterrupted from one end to the other. This means travel time isn't reduced by distance, but by removing interruptions. And when distances collapse like that, what does it change beyond the tunnel itself? Projects like this don't just solve transportation problems, they change how regions function, because distance is no longer defined by physical separation, but by how directly places are connected. Isolated regions become integrated. Trade accelerates, movement becomes predictable. But the deeper impact isn't just speed or convenience, it's control over uncertainty. Weather no longer disrupts movement, geography no longer dictates routes, and time is no longer lost to external conditions. What used to depend on nature is now stabilized by engineered systems, which means infrastructure is no longer reactive, it becomes predictive. Movement happens when it's needed, not when it's possible. And once systems reach that level, they stop adapting to the world and start defining how the world operates. Because at that point, efficiency isn't improved, it's enforced. Infrastructure stops adapting to geography and starts overriding it. What used to be barriers become pathways, even under the ocean. This means natural limits don't disappear, they stop controlling the system. And if natural barriers stop defining movement, what does that leave as a limit? For most of history, infrastructure adapted to the world. Mountains, rivers, oceans defined what was possible. Now that relationship is reversing. Systems are being designed to operate independently of those constraints, not by removing them, but by making them irrelevant to movement itself. And as that continues, distance is no longer defined by how far places are, but by how efficiently they're connected. This means what feels far is no longer about distance. And when distance is no longer defined by how far places are, what is still far?